With the Cielo theorems, we have powerful tools for investigating the internal structure of a given group G. The next step, we want to know when can G be broken down into smaller groups. So by this I mean, when is G a direct or semi-direct product? To start, let's review the definition of external direct product. So here I'll have two groups, H and K. I want to form a new group. For the set, we take the Cartesian product. So I'll have all ordered pairs, element of H, element of K. For the multiplication, we use the natural multiplication, which is to multiply coordinate-wise. Now, with this construction, we're forming new groups from old groups. We want to go the other way. If I have a given group, when can I write it in terms of old groups under the direct product? Now, first thing we have to ask, what are going to be the candidates for the groups H and K if we can do this? So you'll note, if I set either H or K equal to the identity subgroup, then if we had this isomorphism between G and the direct product, we'd have H or K arising as a subgroup of G. So all of our candidates have to occur as subgroups of G. The next step is how do we glue things together? So when I have a direct product, it's clear. When we have a semi-direct product, we know how to do that. It just takes a little bit of work. Now, the game that we're playing, we're calling this the internal direct or semi-direct product. So it's occurring inside of a group that we already have. Now, for internal direct product, here's the result. We have H and K, subgroups of our group G. G is isomorphic to the internal direct product of H and K, if and only if, first, G is equal to the product of subgroups H and K. So this just means we can write every element of G as an element of H times an element of K. Then I'll want H and K as normal subgroups in G. Finally, I'll want the intersection of H and K equal to the identity element. Now, to make sense of all of this, let's note, if I want G isomorphic to this direct product, I have to produce the isomorphism. So what I'll do is, I'll define pi going from G to the direct product. Using 1, I can define pi just on products of elements of H with elements of K. So I'll just send HK to the ordered pair H comma K. Of course, we have to make sense of this. Now note, where do the subgroups H and K go? H is going to go to subgroup H crossed with the identity subgroup, and likewise for K. Now, you'll note, our three conditions just line up with what we're doing with the direct product. First step says we get all elements of the group. Third step says there are no double counting, so there's no overlaps between the two, which is what we would have with a direct product. Finally, this condition says that the elements of K are going to commute with the elements of H, just like in the direct product. Now, for the proof, in the direction going from the direct product to the three conditions, that's straightforward, so I'll leave it to you. In the other direction, I want to show that our map pi is an isomorphism. We need to show a few things. First, we have to show that pi is well defined, meaning it doesn't depend on the choice of H or K. Then we'll have to show the isomorphism property, which means homomorphism, 1-to-1, and on to. For the first step, I want to show that the elements of H commute with the elements of K. To start, I'm going to form the commutator of an element of H with an element of K. So I'll have HK, H inverse, K inverse. And we note the last three terms, we're conjugating an element of H by an element of K. H is normal, so that's going to give us another element of H, say H prime. Because H is a subgroup, H prime is an H. And then we're going to consider the first three terms. Here I'm conjugating an element of K by H, so by the same argument, this element also lives in the subgroup K. So it's in the intersection. By condition 3, our element must be the identity element. If we push the inverses to the other side, we have our result, that the elements of H commute with the elements of K. Now, to get the well-defined property, I want to show that our decomposition is unique. So if we have HK equal to H prime K prime, we'll have to have the H equals H prime, K equals K prime. Then there's going to be no ambiguity when we define our map pi. So for this, same idea. We're going to use the intersection property. If we have this equation here, I can put the H's on one side, K's on the other. This product's in H, this product's in K, and if they're equal, they must be in both. So the only way we can have an intersection here is if we have the identity element. So that means H equals H prime, K equals K prime, and that's our result. Now that we have a map, let's show isomorphism. First, for homomorphism, so I'll say that G is equal to H times K, G prime is H prime times K prime. We just write things out. Now, by our commuting property, I can push these past one another to get the H's and the K's together. We apply pi, so we put them in coordinates, and then we can pull this out as a product, giving us pi of G prime, which is what we want for homomorphism. For one-to-one, because I have a homomorphism, all I need to do is check the kernel. So the only thing I want in the kernel is the identity element of G. Now, if I have some HK going to, the pair identity for H, identity for K, that means, when we apply this to HK, we get the pair HK. So H is the identity of H, K is the identity of K, which means HK is equal to the product of the identity elements. But these are subgroups, so their identity elements are just going to be the identity elements of G. So I get the identity of G out, and we have one-to-one. Finally, for onto, there's nothing to show. This just follows from property 1. So if I'm looking for, we have a fixed HK in our product. I want to find some G such that when we apply pi, we get HK. Well, I could just use G equal to H times K, and we're done. So we have our isomorphism property. For examples, we first choose integers m and n greater than 1 and relatively prime. The statement is that z mod nm is isomorphic to the direct product of z mod n with z mod m. We'll say more about this later, but for here, it's just going to be an application of our proposition. Now, if I want to show this as an internal direct product, we need to find two subgroups and then show that they satisfy the three properties. So I'll let H be generated by M, K generated by N. So H is isomorphic to Z mod N, K is isomorphic to Z mod M. So that's why this is written backwards. For the third property, the intersection is equal to the identity element, which is 0 since we're using addition. If I have an element X, in both of these, we can work over the integers and then pass to modular integers. X is going to be a multiple of both M and N, but because M and N are relatively prime, that means, for instance, N is going to have to divide K in this product. So the X is actually a multiple of Mn. When we pass to modular integers, X is going to go to 0, and we have the identity element. For property 1, so we want to show that every element in our group can be written as a sum of element of H, element of K. Well, we know because M and N are relatively prime, we have X and Y such that X times M plus Y times N is equal to 1. If I want the element J, I can multiply this equation by J, and that'll give us the correct multiples of M and N, elements of H and K, to get to J. So that gives us property 1. Finally, for property 2, if I want to show the normal property, we get that just because our group's abelian. So all of its subgroups are normal. That gives us Z mod NM as this internal direct product. Now, of course, we can get this directly just by noting that the element 1, 1 is going to generate all of Z mod M cross Z mod N. And we know there's only one cyclic group of order Mn, Z mod Mn. So we can get our isomorphism that way. For another example, let's use Cielo Theory. We want to find all isomorphism classes of groups of order 45. Prime divisors of 45 are 3 and 5. Cielo Theory guarantees subgroups of order 5 and 9. If we want to count the number of those subgroups, the rule is, the number divides the order of the group and is congruent to 1 mod the prime. So that means we have unique Cielo 3 subgroup and a unique Cielo 5 subgroup. Because we have unique subgroups of a given order, they must be normal. So we have property 2. And if we want the isomorphism classes, Cielo 5 has to be isomorphic to Z mod 5. Cielo 3 has 9 elements, so that's a square of a prime. So it's abelian and either Z3 cross Z3 or Z mod 9. Now, for property 3, if we take the intersection, Cielo 3 has elements possibly of order 1, 3, or 9. Cielo 5 has elements of order 1 and 5. So they have to intersect in the identity element. So that's property 3. For property 1, I'm going to use, result, the product of normal subgroups gives another normal subgroup. So if I form the subgroup given by product of our Cielo 3 with a Cielo 5, we get another subgroup. 5 is going to divide the order of this subgroup, and 9 is going to divide the order of this subgroup, because we have subgroups of order 5 and 9 in here. So that means we have at least 45 elements, which means we have all of G. So that gives us property 1. Now, we have the internal direct product, so where are the isomorphism classes? If I have Z5 with the Z9, we could use this result to say that we have Z mod 45, so it's cyclic. In the other case, I could put the Z5 with one of the Z3s to give us Z mod 3 cross Z mod 15. And we note in both cases we have an abelian group. Here's the analogous proposition for semidirect products. We have H and K subgroups of G. G is a semidirect product of H and K, using omega. If and only if, we have the following 3 statements. So as before, I have that G is equal to H times K. So every element of G can be written as a product of an element of H with an element of K. We have that the intersection of our 2 subgroups is the identity subgroup. Now we have just that K is normal in G. So I don't need that condition on our subgroup H. With regard to the omega, to make a semidirect product work, what I'll want is omega, a homomorphism from the subgroup H into the automorphism group for K. Then we'll have a definition that sets up the semidirect product. So you can go back and review that. Now, if this homomorphism is trivial, meaning it's going to send every H to the identity map on K, we're just going to get back the direct product. Now, for the proof, same as before, except a few extra details. Going from the semidirect product to the properties, straightforward, so I'll leave that to you. Then in the other direction, going from the properties to the semidirect product, what do we have? Well, as before, we'll use 1 and 3 to show that the isomorphism pi from before is well defined in this context. And that's the same argument. For this business of the elements of H and K commuting, we might not have that anymore. So what we're going to have instead, for the semidirect product, whenever I conjugate an element in K by an element in H, we're going to use the automorphism going from H to aut K to tell us what to do with K. So another way to think of this, if I want to switch H and K, The penalty is to apply this automorphism to K. Now, we have well-defined, so we have the three properties that we need to show. Okay, homomorphism, one-to-one and onto. The one-to-one and onto properties are going to be the same as before, so we won't repeat those. So now all the focus is on the homomorphism property, and for that you need to review the definition of the semidirect product. Now, if I take a product, okay, G times G prime, okay, so I'll call G written in the form HK, G prime written as H prime K prime. Take the product and apply pi. Okay, we write that out. Then I want to get the H terms and the K terms together. So I'm going to do the switch, and we note to do the switch, we're going to have to take the penalty by putting in the automorphism. Now, another way to think of that is I could just insert an H prime inverse to get the conjugation to appear. So this conjugation here is going to go to omega sub H prime inverse acting on K. This is an automorphism of K, so this element's in K, and we've separated the elements into H elements and K elements. Now we know how to use pi. First coordinate is going to be H prime. Second coordinate, okay, we have our automorphism on K times K prime. If we split into the product, okay, we follow it out until we get to this step. And now this step, what we do is we just go look up definition of semidirect product. And then we see that that's going to give us the same as what we have here. So we have the homomorphism property. We have one-to-one and onto, so we have an isomorphism. For an example, we start with a group of invertible 2x2 matrices with elements in Z mod 7. In there, we'll have the subgroup G, given by matrices of the form A, B, 0, 1, where B is in Z mod 7, A is in the multiplicative subgroup 1, 2, 4. Note, 2 times 4 is 8, which goes to 1. So we're going to have a Z mod 3 here. We want to express this subgroup as a semidirect product of two of its subgroups. Now, if we count, we have 3 times 7, or 21 elements. Cielo Theory says the Cielo 7 is unique. For the Cielo 3s, we can have 1 or 7. If I let B be equal to 0, we have a Cielo 3 going down the diagonal. If we conjugate, we can get other Cielo 3s. So it has to be 7. Now, this means we have a normal subgroup given by the Cielo 7 subgroup. Okay, so that's going to be our K. For our H, I'm just going to take the Cielo 3 going down the diagonal. So if we take the intersection here, we're going to have the identity subgroup. So that's condition 3. For condition 1, if I take an H times a K over all possibilities, we get all of G back. So we have all the conditions for a semidirect product. So our subgroup is a semidirect product of a Z3 and a Z7. All we need to know is the homomorphism that glues things together. To get that, we just take arbitrary element from our Cielo 7, arbitrary element from our Cielo 3, and conjugate. What happens here, if we have a B here, conjugating with an A here, it's just going to send B to A times B. So the homomorphism is given by, omega A on B is just A times B. So multiplication. So that completely describes our semidirect product. Final things to note. Direct products and semidirect products are not going to answer all of our questions. So for instance, for the quaternion group, you can never express that as a direct or semidirect product. The problem, every subgroup of the quaternion group's normal, so that's good. The problem is, if I intersect any two non-trivial subgroups, we get something that's non-trivial. So we're never going to have condition 3. We also have simple groups. Problem here, recall, simple group, the only normal subgroups are the identity subgroup or the group itself. So these are going to be resistant to study by direct products or semidirect products. They're also resistant to forming quotient groups. So somehow we're going to need other methods to study these.